Welcome to section 9.1, describing acceleration. From the last chapter, you are, I suspect, well familiar with this concept of uniform motion. You're looking at a putter, of course, hitting a lovely little golf ball towards a hole. And of course, the golf ball misses. But what really matters here, believe it or not, is this data. In the first 0.2 seconds, golf ball moves from 1.5 to 1 meters. And then the next 0.2 seconds, it moves to 0.5. The next 0.2 seconds, it goes by the hole, which of course is the point of reference. We'll call that 0 meters. The point here is this is uniform motion. Equal displacements are being made in equal time intervals. Uniform motion. So an object traveling with uniform motion has equal displacements in equal time intervals. This little section is all about description of what is involved in change in velocity and acceleration. The last section you do in your motion unit will be on calculating acceleration. I have to emphasize that you really will find the calculation side of acceleration much easier if you really have a good grasp on the descriptive aspects. So we continue. Not all objects, of course, exhibit uniform motion. Take, for example, the space shuttle. So this space shuttle is not uniform. Within 60 seconds of launching, the space shuttle is traveling at 350 meters per second and is 16 kilometers above the Earth. How's that for displacement? During the next 60 seconds, the space shuttle increases its speed by over 1,200 meters per second and travels an additional 30 kilometers away from the Earth's surface. Obviously, this is not equal displacement in equal time intervals. This is not uniform motion. The point is, in order to launch the space shuttle correctly, scientists need to be able to analyze and predict motion that is changing both in speed and direction. So an object traveling with non-uniform motion, you're going to notice a couple of things, 2 or 3 things. They have different displacements during equal time intervals. They take different amounts of time to travel equal displacements, and they have a continuously changing velocity. So those are 3 important points. I'm going to repeat them. Have different displacements during equal time intervals, take different amounts of time to travel equal displacements, and have a continuously changing velocity. So you try it. This young lady sliding into home plate. Would you say she's undergoing uniform motion? No. She is undergoing non-uniform motion. As she slides, the velocity of the player is continually changing. She's slowing down, therefore her motion is non-uniform. Okay, the big question moving forward is to now consider what factors make this a change in velocity. And the fact is there are 2 factors that are involved in any change of velocity. A change in velocity, delta V, occurs when the speed of an object changes and or its direction of motion changes. Notice there are 2 possibilities there. So a change in velocity can be calculated by using this lovely formula, delta V. That means the change in velocity is equal to the final velocity minus the initial velocity. And don't forget, these lovely little arrows tell you they're vector quantities. So they specify direction. Direction is really important because direction is one of the things that characterizes a change in velocity. So if the change in velocity is the same sign as the initial velocity, plus or minus, then the speed of the object is increasing. So it could be going backwards, it could be going forwards, but if the change is in that same direction, plus or minus, we say it's positive. If the change in velocity is the opposite sign, again plus or minus, of the initial velocity, the speed of the object is decreasing. And there's a third option. If the change in velocity is 0, the object is traveling with uniform motion. And yeah, there wouldn't be any change in velocity. So take the dragster. If forward is designated as positive, we would say this dragster's change in velocity is positive. It's in the forward direction, in the same direction as the change in velocity. On the other hand, space shuttle landing, if forward is again designated as positive, the landing shuttle with the parachute has a negative change in velocity because it's in a different direction from the forward positive direction. Eventually you get your brain to wrap around this positive and negative change in velocity. The point is, change in velocity is very important because it's part of the definition of acceleration. Acceleration, and the abbreviation is lowercase a, is the rate of change in velocity. Anytime you see this word rate, you know you're talking about time. Over time, how does the change in velocity change? So this change in velocity can be due to a change in speed, or it can be due to a change in direction. So two objects with the same change in velocity can have different accelerations. Now that sounds weird, because take two cars, one an old jalopy, one a dragster, they can actually have the same change in velocity, but have very different accelerations. Velocity being equal is true in this case according to the formula for change in velocity, and you're welcome to plug in some numbers to try. But of course this is true because acceleration describes the rate at which the change in velocity occurs. Suppose both these vehicles start from rest, they both speed up to 60 kilometers per hour. If you use that lovely little formula for change in velocity, they're going to both have the same change in velocity. But since the dragster can get to 60 kilometers faster, 60 kilometers per hour faster than the old jalopy, the dragster has a far greater acceleration.
Hi-ho.
Hi-ho. Positive and negative acceleration. The direction of the acceleration is the same as the direction of the change in velocity. Acceleration that is opposite to the direction of motion is some kind, it's called deceleration. So a couple of examples of acceleration. It's all right, Mr. Flink was just visiting, and of course if you have any questions about positive and negative acceleration, you make sure you knock on his door. He's in there, I guarantee you. So an example of acceleration would be a car speeding up in the forward direction. If we designate the forward direction as positive, then the change in velocity is also going to be positive, and the acceleration is positive. Take this car. The light has just turned green. It's moving in the forward direction. Velocity is changing in the forward direction. Therefore, the acceleration is positive. Of course, you'll notice these lovely little page numbers. These page numbers refer to the alternative textbook pages where you can get far more elaboration on each of these concepts. Anyhow, to continue with positive and negative acceleration, let's look at a car slowing down in the forward direction. If we designate the forward direction again as positive, then the change in velocity is negative. And if that is true, therefore the acceleration is negative. So this time, car is speeding along happily, velocity in the forward direction, and then the light changes to red, and the change of velocity is going to be in the opposite direction, negative. Therefore, the acceleration is negative. And of course, where you see this is if you actually plug it into the equation using the numbers, you will actually see that this is in fact true. There is another possibility, of course. Possibilities are a car speeding up in the backward direction. Now, if we designate the backward direction as negative, then the change in velocity is also negative. And that, of course, is what it looks like in terms of the actual calculation. The final velocity minus the initial velocity equals 3 meters per second backwards. This means that the acceleration is negative even though the car is increasing its speed. So this 3 millimeters per second backwards, the backwards is the vector part of the equation. Remember that positive and negative are simply referring to the directions. That's where the backwards comes in. So that's what it looks like. The initial velocity is -1 backwards, the final velocity is -4. So -4 minus -1 equals -3 meters per second. And again, we've said that negative means backwards. So what happens if a car slows down in the backward direction? If we designate the backward direction as negative, then the change in velocity is positive. And this scenario looks like this. So we go from -4 meters per second initially, and we brake or slow down to -1 meters per second. This means that the acceleration is actually positive, even though the car is decreasing its speed. And again, remember that positive and negative simply refer to direction. Car is slowing down in the backward direction, but it's in the same direction as the change in velocity. You're going to notice throughout most of these little presentations little links to take the section 9.1 quiz. Highly encourage you to take that link, do a little practice quiz on this, and then move on to the study guide for describing acceleration.